Alright, so we're going to take a look at section 4.4, and this is the last section in chapter 4, and it's on radical functions. So pretty much the next three sections we look at, which is going to finish the algebra part of the class, we're going to look at a different function every day, except the last function we'll spend 2 days on. So we got radicals, then we got exponentials, and then logarithms. What we're going to focus on is a little bit of graphing, okay, how to graph each one of those by hand, and then a little bit of algebra, like how do you solve an equation that has like a radical in it, okay? Or exponential or log. Okay, so we'll do each one. Okay, these are examples of radical equations. Okay, what makes them radical is that square root symbol or the cube root symbol. This one, the first one, that's more typical of the kind of stuff we'll be graphing and looking at. The one on the right, that's a little more advanced, not something we would see at this level typically. Okay, but they are both radical functions. So any expression of the form that's nth root of a could be a square root, cube root, fourth root, any root. So if you have a root, right, I'll explain what this is, but that number right there is called the index, and it tells you the root you're taking. The index, or the n, has to be a number bigger than 1, okay, and it's an integer. So there's no such thing as like a 2.5 root. You can do a square root, you can do a cube root. There's nothing in between. So the index is always an integer greater than 1. If you don't see an index, like this one, I didn't put a number where I just circled, we always assume it to be a 2. If you don't put a number, it's a square root. So that number that's in the kind of the V shape of that symbol, that's called your index. What you put under the symbol, that's called the radicand. Okay, the radicand is what you're taking the root of. So if I said to you, what's the square root of 4? 4 is the radicand. The actual symbol, we just call that the radical sign. Kind of looks like that check mark with a horizontal line on top. That's a radical sign. So any questions on those terms? Radical, radicand, index, radical sign. All right, so the whole thing, the whole expression together, that's a radical. And it's made up of 3 parts. The radical sign, the index, and the radicand. Alright, I already said that earlier, but if there is no index, you always assume it's a 2. Okay, we're doing a square root. Now, this is going to come up in the next couple lessons, but sometimes we don't want to write something with the radical sign. Okay? There is a way that you can write things without a radical sign, and it still means the same thing, but you can use an exponent instead. So, if you wanted to write something as a square root, and you don't want to use the radical sign, that's okay. You don't have to use it. You can raise it to the 1/2 power instead. All right, so if I take like the square root of 16, I get 4. If I take 16 to the 1/2 power, I get 4. It's exactly the same thing. So if for some reason your calculator didn't have a square root button, you could raise it to the 1/2 power and it's the same thing. How about a cube root? Does anyone have a guess what power I could raise something to, and it would be the same as taking a cube root?
The power of 1/3.
Yeah, to the 1/3 power. Okay, so raising something to the 1/3 power is a cube root. 1/6 power, 6th root. 1/20th power, 20th root. It's just basically 1 over the index. So how about a 5th root? What exponent would I use for a 5th root? 1/5. Now, out of all these examples, the only one that it actually even really makes sense to do this on is the last one. Because when I do it, I still have the radicand, but now it's x to the 4th to the 1/5. And there's a rule, whenever you have a power to a power, you can do something with the 4 and the 1/5 to put them together. Yes, you can multiply them together. So by writing the 5th root as a fractional exponent, it allows you to put them together. So x to the 4/5 power. So any questions on that, especially that last one, where I did the power to a power and multiplied them together? Okay. We're not going to see a ton of fractional exponents in this section, but it is going to come up. All right. So if they ask you to solve an equation and they specifically say find the principal nth root, well, principal means they want one answer. When you take roots, there's multiple answers. Principal means they want just one. So, for example, like if I asked you the square root of 4, what are the two answers for that? Yeah, Jade? 2 and negative 2. 2 times 2 is 4. Negative 2 times negative 2 is also 4. In fact, a root has as many answers as the index. A cube root has 3. A 4th root has 4. A 10th root has 10 answers. What gets a little tricky is they're not all real. Some are real, some are imaginary. With square roots, they're both real. So that's easy. Okay. But the point is, if they say principal, they want a single answer. So, if you wanted to find an odd root, okay, so if I was trying to explain to somebody how to do a cube root, and they had no concept of roots, didn't understand what a root meant at all, but they understood exponents, I would explain it to them this way. Right? So let's say you want to find the cube root of 64. And somebody looked at that and they're like, I'm not sure what that means. I don't know what to do. I'd say, okay, well, you're finding a cube root. So in this case, your index is 3. And you're finding the cube root of 64. So it equals something. Right? So I would say, all right, if you can figure out how to rewrite what I just wrote in this equation, we can kind of think through it. So n is 3. A is 64. Watch what happens if you plug those two numbers into this equation. X we don't know. N is 3, and A is 64. All right, so if someone didn't understand a cube root, I would say, okay, think of it this way. There's a number you can raise to the 3rd power and get an answer of 64. If you can figure out what that number is, that's the answer to the question. So what would it be in this case? What number would you raise to the 3rd power to get 64? Yeah. 4, yeah. So the cube root of 64 is 4. Okay. So when you're finding an odd root, just think of it this way. Some number to a power gives you 64. Or whatever they're asking you to find. Now, if it's even, we just did an example earlier with a square root. Okay. We got 2 answers. Square root of 4 was 2 and negative 2. For a principal root, I'm looking for the answer that's non-negative. I do not want a negative answer if they specifically say find the principal root. And how would you know if they want a principal root? You would see something like this. That question implies principal root. If they want the positive and the negative, you'll see this. Plus or minus in front of the root. This means they want both answers. Positive and the negative. Just the positive. If you type that in on the calculator like that, it's exactly what it gives you. It'll only give you 2. If you throw a negative in front, it'll give you the negative 2. Okay, so any questions on that one? Now, the other thing I wrote right here is a has to be greater than or equal to 0. So for square roots, just as an example, but it works with any even root, why does the thing you take the root of have to be greater than 0? What would happen if it wasn't? Yeah.
You get non-real numbers.
You get non-real numbers, you would get imaginary. So when you're dealing with even roots, the number under here always has to be a positive. That's not true for odd roots. Okay. We did the cube root of 64. I can do the cube root of negative 64. The answer is negative 4. Negative 4 times negative 4 times negative 4 is negative 64. So negatives are okay with odd roots, but negatives are not okay with even roots, unless you're doing imaginary. Okay. Okay. So what I want to do is I want to take some square roots, and I want to see when I take a square root if the answer gets smaller or if it gets larger. Did anyone have a general thought when you take the square root of a number? What happens to it? Smaller? All right, so let's try an example. I'm going to start with 4. We already did that one. Square root of 4 is 2. Okay, so I agree. That one got smaller. Let's try the square root of 18. That's not one I can do in my head quickly, so I'm just going to get a decimal for it. We get 4.24. It got smaller. How about the square root of 1? Any thoughts on that one? Square root of 1? Yeah. 1. Didn't get smaller. Stayed the same. So maybe the answer is when you take a square root, it stays the same, or it could get smaller. Okay? Let's try this one. Square root of a half. If I do 0.5 and take the square root, I get 0.71 if I round it. Got bigger. And let's just do one more. 0.2. Square root. 0.45. It got bigger. So the answer is, does the square root get smaller or larger from the original number? It depends. Based on that chart, anyone think they can predict like a pattern? Like when you take a square root, when it gets bigger, smaller, or stays the same? Yeah?
It seems that if it's a decimal, it'll get bigger.
Yeah. If it's a decimal, if it's between like 0 and 1, you take the square root, it gets bigger. If it's exactly 1, it stays the same. If it's larger than 1, it gets smaller. And I think I have that. Did I write it? No, I didn't write it out. But that is just something I wanted you to notice. So square roots don't always get smaller. Now, if I asked you, let's just take the square root of 1. Devin, what's the square root of 1? 1. How about the fourth root of 1? What times itself 4 times gives you 1? 1. The sixth root of 1, the eighth root of 1. Any even root of 1 is always 1. Okay. Now, what about if I try 0? What's the square root of 0? Oh, Nathan?
It's really, you can't count that, I'm pretty sure. No, it's
So you can't find 2 numbers that multiply together to give you 0 that are the same?
Other than 0.
So 0 times 0 is 0?
Itself.
So that's the square root of 0 then. 0 times 0 is 0.
0 to 0 power.
So the square root of 0 is 0. How about the fourth root of 0? What times itself 4 times, same thing, would give you 0? 0. 0 times 0 times 0 times 0. So there's a couple roots here that always come out the same. If you take an even root of 1, you always get 1. If you take an even root of 0, you always get 0. So what I'm showing you is that these 2 points are common to all even roots. If you plug in 0, you get 0. You plug in 1, you get 1. Okay, let's look at let's look at a picture. So I'm going to graph the square root of x, and then to do a fourth root, put in the index, go to math, and it's the fifth option down. So that's something new we haven't done before. Okay, let's hit zoom 6 and see what it looks like. There's your square root. And there's your fourth root. Okay, it's kind of hard to see unless I zoom in a little bit. So I'm going to zoom in right there. So I'm going to set my minimums at 0. I'll set my maximum at like 2 and 2. I think that should be good. So let's go 0 to 2 and 0 to 2. If I zoomed in enough, you should be able to see it. Okay, it goes right through 0, 0. That's the square root. And here's the fourth root. It goes right through 0, 0. And they both go through the point 1, 1. Notice, though, they switch places at 1. Which one is bigger and which one is smaller. After 1, the blue graph is above. Before 1, the blue graph is below. And that's because of the idea in this table. All right? At 1, they're equal. But then square roots kind of change their behavior when you're between 0 and 1, and then when you're after 1. So that's what you're kind of seeing in that picture. Things change at 1. All right? And if I were to graph a sixth root, I'll just show you what that would look like. It's going to follow the same pattern. The sixth root is above everything until it gets to 1, 1, and then it's below everything. So the larger root that you take, if you look at big numbers, the larger the index, the smaller it is. It's below everything. Before 1, it's different. The larger the index, the higher the root, okay, between 0 and 1. So they all go through this point, and they all go through that point. Now, if you look at them, they only go in one direction. Okay? They don't go into the negatives. When I zoomed out, you could see they all started at the origin. So the domain is 0 to infinity. We said that earlier. You cannot plug negative numbers into even roots. It doesn't work. And the range, well, these graphs don't go down forever. They all start at the origin, but they do go up forever. Okay? If you look at, just focus on y1. That's the square root. If you plug in a bigger and bigger number, y1 is going to keep getting bigger and bigger. It's not getting bigger fast, but it's never stopping. It's not like all of a sudden it's getting close to like 2.999999999, and it's like not going above that. It just keeps growing. So it goes up forever, okay? But it doesn't go down forever. So the range is 0 to infinity. Yeah.
Wait, so why can't you plug negative numbers in? Like, I know it wouldn't look any different, but
Because the answer would be imaginary.
if you, oh wait, I was thinking about that.
So if you tried it, like if I go second, square root of -3, it's not that it doesn't have an answer, it's just the answer is not real.
Oh,
So we're not going to look at that.
oh yeah, no, I was thinking about that wrong.
Okay, so any questions on the domain and range of a square root function? Big thing to, or actually not even square root, anything with an even index. So big thing to remember, even index functions start at one spot and they go in one direction. Okay? It doesn't always have to go to the right. I could mirror image it and I could make it go to the left. Okay? So if you mirror image it, it'll go a different way, but they always start in one spot and they only go one way. Okay? That's even index roots.
So even, like, only if you're working with even 0 and 1. Like, they'll always go through 0 and 1? Or is it...
All even roots.
Okay.
6th root, 8th root, 22nd root, 50th root, 108th root. They all go through the point 0, 0, and they all go through the point 1, 1. Yep. the basic root. Now, like any function, I can take this and I can go like this, plus 1. That's going to shift it up 1. Well, now it won't go through those points because you've done something to it. See how much higher it is now? It's been shifted up. So what I'm saying when they go through the point 0, 0, and 1, 1, I'm just saying if you don't do anything to them, you don't move them around, you just leave them the way they are. Okay. But now it's been shifted up. Okay. Let's look at a couple examples of some odd roots. So now instead of square root, I'm going to replace that with a cube root. Okay. And I'll do a 5th root. And I'll do a 7th root. Really, if you do 2, that's enough to see a pattern. But I'll do 3 different ones. And I'm going to do zoom 6. And what do you notice right away that's different about an odd root compared to an even root?
It goes in both directions.
It goes in both directions. Okay? So what we say here is the odd roots have like a center point, and they go out in each direction from that center point. Now it's kind of hard to see what they're all going through, but if I zoom in near the origin, I think you'll be able to tell what's going on. So there's your cube root. Here's your 5th root. And there's your 7th root. Okay, try to make that a little bigger. And I want you to try to tell me what points they all have in common. Anyone think they see a coordinate that they all go through? Yep, Sean.
0, 0.
Yep, they all go through 0, 0. My cursor's on top of it, so it's hard to see, but they do. Any other points besides 0, 0? Yep.
-1, -1.
-1, -1. Yep. They all go through that point, and then there's one more. 1, 1. So odd roots always have those 3 points in common. If you don't mess with the root. If you take and you shift it up or down, well, now you've changed that. But we're just talking about the basic function. Yes?
With an even root, will you ever get that like snake kind of thing that I had?
No. No. Even roots always look something like that. Or a mirror image of that. This way, or that way. They always have that curve to them in one direction. Okay. And big difference, I already mentioned it, but the domain, it goes left and right forever. Okay. So if I zoom back out so you can get kind of a bigger view, it never stops going left, it never stops going right, never stops going up, it never stops going down. Okay. If I zoom out further, you just see it going up and down more and left and right more. Okay. So domain and range, -infinity to infinity for both. Okay. Any questions on that? All right. So, with each function we study, we're going to look at the transformations. We've already done this with parabolas. We've done it with rational functions. We've done it with all the functions. So I'll quickly go through what A, B, and C do. But 2 of them are shifts. 2 of them are stretches. 2 of them are horizontal. 2 of them are vertical. It's exactly the same as everything we've done before. Whenever you're dealing with the stuff inside the function, that's your horizontal. So stuff that's inside. In this case, inside means under the root. Okay? Inside. Outside stuff is vertical. Whenever you're adding, it's a shift. Whenever you're multiplying, it's a stretch. So here, I don't know if I have enough room. Yeah, I'll squeeze it in. So here I'm adding inside. Inside means horizontal. Adding means shift. B, it's inside. That means it's horizontal. But it's multiplying. That means it's a stretch. Now, it could be a compression. Depends on the number. So when I say stretch, it could stretch or compress. C, that's multiplying, but you're outside. So it's a stretch, but it's vertical. So stretch. And D, you're adding, which means it's a shift, but it's outside the root, which means it's vertical. So vertical shift. Sorry. Okay. Now we got to be careful because the horizontal stuff always does the opposite of what you would expect. So B and A do the opposite. So when I see a plus, it's going to be like plus A, it's going to be a horizontal shift to the left. Okay, plus moves things left. If we see a minus A, it moves things to the right. And that's the opposite of what you would think, like if you think of a number line. That's how it works. A and B always do the opposite. So what does that mean for B? Well, you might think if you put a big number in for B, like 20, oh, 20 is going to make it 20 times bigger. No, 20 would actually make it 20 times smaller. So it would compress it by a factor of 20. If you put in a number like 1/3, a small number for B, small numbers actually make it bigger. So a number like 1/3 would actually stretch the graph out 3 times as much. Okay. If you put a 1/4, it would stretch it 4 times as much. 1/20 would stretch it 20 times as much. Okay, so A and B do the opposite. C and D don't. They do exactly what you would expect. If you put in a big number for C, it stretches your graph bigger vertically. If you put in a small number for C, it would compress it. If you put in a positive number for D, it goes up. A negative number for D goes down. So C and D are exactly what you would expect. Now, does anybody remember what happens when you put a negative in front of the B or the C? That causes our graph to do something. Yep. Flip. Okay. Which flip? Well, look at where it is. If the negative is inside the function, that's where the horizontal stuff is. It would do a horizontal flip. What does that mean? A horizontal flip looks like this. If that's your shape, that's a horizontal flip. It's a left to right flip. If you put a negative with C, that's outside the function. Anything outside is always vertical. So a negative outside causes a vertical flip. That's a vertical flip, up to down. So you can describe it as a vertical flip, or some people say reflect over the x-axis. It means the same thing. Horizontal flip means you're actually mirror imaging over the y-axis. So that's a breakdown of what each letter does, and then what the negatives would do as well. So again, it's similar to all the transformations we've studied all year. You don't really need to write that, but I'm just letting you know. So most problems I have you do, they're not going to have every single number in them. Okay? In fact, this one only has one transformation. So example 1 says, explain how to sketch g of x, given that you're starting with this. Okay, your basic graph is square root of x. I want to know how to sketch the square root of x minus 2. Okay, so you'd start out by saying to sketch g of x. And now I need to explain what I would do. What would you do with the square root of x to turn it into g of x? Yep, go ahead, Emily.
You shift to the right too.
You would shift it to the right 2, yes. So that -2, that's a horizontal because it's inside. It's addition or subtraction, so it's a shift. And I think, okay, horizontal always does the opposite. So you just have to remember it or put it on your reference sheet. So it's going to go right 2. That's it. All right, let's look at this one. So we start out the same way. To sketch g of x, all right, and then describe what you do. So how about Alec, how would I sketch g of x? Actually, we did g of x, I'm sorry. H of x. Let's try that one.
You would shift it to the left 3 times, right?
Yeah. So I see, okay, inside the function, horizontal, plus, it's a shift, and it's got to do the opposite because it's a horizontal. So I think plus, it's going to go left 3. Okay. Let's look at this one. Now, k of x is not set up the right way. Look under the root. What always comes first? The number with the letter or the number without the letter? The letter. The number with the letter always comes first. The thing without it comes after. So how could I rewrite that so it's in the order that we're used to? Yep.
Negative x plus 3.
Yep, negative x plus 3. Now we've got 2 things going on. It's very similar to the last problem, but this negative is going to cause one extra thing to happen that we just talked about. Okay, so to sketch k of x, I'm going to do it this way. First thing is you still have to do the shift. Okay, how do you know the order to do things in? That's why I used A, B, C, D. You do A, B, C, and then D. You always list them in that order. Okay. So the first thing is A, plus 3. Already did a plus 3. It's going to shift left 3. Shift square root of x, left 3. And now we have a negative in front of the x. Now, the number is not there, but what number is it like having in front of the x? It's like a -1. So really, there is no stretch or compression. You're stretching by a factor of 1. But what is the negative going to cause it to do? Flip, and then it's going to flip which way? Because we can flip horizontally or we can flip vertically. Yep.
Horizontally.
It's going to flip horizontally. So flip, or you could say reflect. Flip horizontally. What does that really mean? Reflect over y-axis. Okay, I know it's weird. Y-axis is vertical, but that's how a horizontal flip works. It's over the y-axis. Mirror image. That's it. Any questions on that one? I'm not going to go through the whole thing, but what would happen there without writing it all out? That would be a shift up 6. How about if I did something like this? 2 square root of x. What would that do to my graph?
Wouldn't that be a vertical stretch?
Yep, that's a vertical. It's on the outside. It's multiplication, so that means vertical stretch. And vertical does exactly what you would expect. It does stretch it 2 times as much. So if you're kind of like, well, what does that really mean, a vertical stretch? If that's your original, then a vertical stretch is something like that. It stretched it out
So
vertically.
it's just like magnified, it's not like...
Well, it's a stretch. So I guess it gets bigger. Like that's a stretch. That would be a vertical compression, like that. I kind of squished it. And then horizontal would be the other way. Okay, so when we're sketching radical functions, we want to make sure that we always sketch the point that corresponds to 0, 0. For an even root, that's a start point. It would look like this. For an odd root, 0, 0 is the center point. It would look more like this. 0, 0 would be right there. So if you're doing an even root, 0, 0 will be a start point. If you're doing an odd root, it'll be a center point. Doesn't matter which one it is, you find it the same way. Okay? And this is how you find it. If you shift up, down, left, or right, 0, 0 is going to move. Where is it going to move? Well, first you got to figure out where the x value goes. Then you can find the y value. To find the x value, set what's under the root equal to 0. Okay, so whatever you have under the root, just set that equal to 0, solve it, and that's your x value. Now, once you have the x value, you're going to have a formula like this. If you know the x value, all you have to do is substitute it back in, do out the arithmetic, and that'll give you the y value. And I think as we go through some problems, you'll see a shortcut to that. We'll do that, and you'll see what happens. Now, that's just a single point. That just gives you the starting point or the center point. We still need a few other points. So if you're dealing with an even root function, you can only pick other points in one direction. If you try to pick points that go the wrong way, you're going to get imaginary answers. Okay, it won't work. For odd roots, you do have to pick a few points that go in each direction. I would say for an odd root, maybe 5 or 6 points. That's probably good enough. For an even root, you probably don't need as many because it only goes one way. So maybe you can get away with 3 or 4 points. All right, so that's what I'm saying right here. Include points to the left and the right if it's applicable, because some only go in one direction, to get a better idea of the curve. Okay. And the easiest way to do that is to use the table on your calculator. Just type in the problem, second table, and just get a bunch of points off your table. If you don't have a graphing calculator and you need to do it by hand, you can. You're just going to have to plug in everything by hand and do it out with a calculator. Okay, so let's try to sketch this one. Okay, what I'm going to do, even though it's not part of the problem, is I'm just going to verbally list to you all the transformations here, just to make sure we understand what's going on. If I wanted to think about this from transformations, I would think of the problem this way. It just makes more sense to me that way. To do what we're about to do, you don't need to rewrite it that way. But this is going to be a horizontal shift, 3 units to the left. This 2 would be a horizontal compression by a factor of 2. Remember, it does the opposite. Big numbers actually make it smaller. The negative would cause a horizontal reflection. The 2 would be a vertical stretch by a factor of 2, and the +1 would be a shift up 1. So there's 5, 1, 2, 3, 4, 5 transformations. That problem almost has every single thing in it you could have. The only thing it didn't have is a negative out in front. All right. So I just want to make sure we're okay with that. Any questions on the transformations I listed? Right, so let's make our sketch. To find the x value, set the radicand equal to 0. There's your radicand. 3 minus 2x equals 0. Okay, I would just add the 2x to the other side. And Emily, what would I divide by to get x alone?
2.
There you go. Divide by 2, divide by 2. It's gone. So my point is going to be starting at 3/2. Actually, I should be careful. We're doing an odd root. Is this going to be a start point or a center point? Center, right? This is going to be a center, and we're going to go in each direction. Now, to find the y value, use substitution. Plug this back in. Well, when I plug 3/2 back in, I already know what the circled part is going to be. What is the circled part going to come out to? 0, because I purposely found this number that makes this 0. So this whole part is 0. What's the cube root of 0? 0. And what's 0 times 2? 0. So the only part that really matters, that's why I said you'd probably see a shortcut eventually, is that plus or minus number. That's your y value. So when I graph this, there's my center point. 3/2, 1. Okay, so I'll let me get a piece of graph paper. So 3/2, that's 1.5, 1. Okay, now I'm going to use my calculator, type that in, and get some more points. So let's put in, okay, if you have anything else in there, you can just get rid of it. 2 times, and there actually is a button for cube root. So the only roots on the calculator that have direct buttons are cube root and square root. And if you go to math, the fourth option down is a built-in cube root button. Any other root, you got to do it the way I showed you earlier, though. So it's the cube root 3 minus 2x. Now, before you hit +1, hit your arrow to the right. That gets you out of the root. Otherwise, the +1 would be underneath. And then it wouldn't be a vertical shift anymore. You'd be able to combine it with the 3. Okay, so I'm going to go to second table. And I like to just check the center point, make sure we got that right. So the center point was 1.5, 1. Let's see. Yep. So we've got the right y value for the center. Now I'm going to just put a bunch of points in the table, and then I'm just going to copy and paste my table and look at it. So let's go to 5 and 10. I'm just stopping at 10 because my graph paper stops at 10. Let's go -5, -10. Okay, that should be enough points. So 5, -2.8. 2, 3, 4, 5. Okay, so we're down about there. 10, we're at -4.1. So 10, about right there. 1, 2, 3, 4.1. Yeah. -5, 5.7. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.7. And -10, about 6.7. 1, 2, 3, 4, 5, 6.7. Okay, so that's pretty good. I can see the curve. I mean, maybe I would want to get one more point, like in there, but I can kind of see what's going on. And so it's not perfect, but if I hit graph, it should look pretty close. Might be a little steeper of a curve, but that's the basic idea. Looks pretty close. Notice in here, it gets so steep that the calculator can't even connect it. It should be connected. There shouldn't be any gap in there at all. So, any question on sketching an odd root? Okay. How about on sketching an even root? Does anyone want me to go through an even? Yeah. Okay. So we'll take a look. We'll take a quick look at it, and then we'll finish up with the last thing. Set your radicand equal to 0. Move the 3x to the other side. And there's your x value, 4/3. Now, this is an even root. Do we have a start point or a center point? Start. So what that means is you're only going to be able to pick x's either bigger than 4/3 or smaller. If you pick the wrong way, you're going to get imaginaries. So it'll be very easy to tell. You type it in, if it says error, you went the wrong way. All right. Now, plug that back in. That's 0. 4th root of 0 is 0. 0 times 3 is 0. 0 minus 2 is -2. There's your start point. 4/3, -2. Any question on the start point? All right. So now I'm just going to type that in and get some more points. I'm not going to graph this one. I'll just get all the points you would need, and then I'll assume you guys could just plot them if you had to. So we got 3, and then messed up. 3 times 4, math, 5. So 4th root of 4 minus 3x minus 2. All right, so let's try 4/3. Okay, I can already tell which way I should go because I'm seeing some errors from the previous problem. Bigger numbers give me imaginaries. So when I go 4/3, I'm okay, -2. But if I go bigger than that, it's the wrong way. So this graph is going to head towards the negative numbers. So 1 would be a good point, maybe -2, -5, -10. Okay, so besides this one, if you graph those 5 points, you'll get a pretty good sketch, and it's going to look something like roughly like that. But if you graph those 5 points, you would see that. Questions on that? Okay, so last thing we're going to look at is solving an equation. So for this, you don't need a graphing calculator at all. So to solve a radical equation, we have to get rid of the radical. A radical is a function. That was the very first thing. It was right in the title. Radical functions. So the only way, if you have an equation with a function, if you want to get rid of it, you need to use a function that's the opposite. So if you had square roots, what function is the opposite of a square root that cancels out square roots? Rebecca, do you know what function would cancel out a square root?
Second power.
Second power, yeah, squaring. So if you see a square root in a problem, you're going to square it to cancel it out. If you saw a cube root, you would. So whatever root you have, you use that power, and that cancels it out. So the way we have to do it is you've got to get the radical alone on one side. This is an example of one that's alone. Square root of x plus 2 equals 8. The radical is all by itself. Here's an example of one that isn't. Now you've got something extra on the same side as the radical. You need to move that first. So in the problem up here, I would subtract 3 from both sides to start. Okay. So think of that radical as a box. You want to get everything outside of that box on the other side. Unless they give you a problem where it already is set up that way, then you're good. All right. Now, if you have a root, square root, you're going to have to square. How many times you have to do it depends on how many are in the problem. If you have a problem like this, This has 2 roots in it. You're going to have to square twice. This is a problem with 1 root in it. It's not a square root, it's a cube root, but you're only going to have to cube once. This one is a lot easier, well, not a lot, but this one is a little bit easier than the next one. Okay, anytime you square or cube or solve both sides by raising to a power, check your answers. Because you may have created an extraneous solution, which means not because you did something wrong, but you created a new answer that does not work in the original problem. So you got to check your answer. Okay, so let's see if we can solve this one. So step 1, get the radical by itself on one side. Is the radical by itself here? Sam?
Yeah.
Yeah, there's nothing on the outside of that radical like this. It's not like you got to divide each side by 5 or anything like that. It's already by itself. So I've got a cube root. What am I going to do to both sides to get rid of the cube root? Connor?
You cube down.
I would cube it. So I'm going to cube this. That's the easy part. This and that all cancel out. X squared minus 2x plus 2 equals. You can't just do it on one side, you have to do it on both. Now, that's a cubic equation. So unless something special happens, we're going to get stuck solving that. We don't know the cubic formula. We know the quadratic formula. So something special has to happen. So let's hope that something special happens. When we solve a quadratic, what number do we try to get it equal to? 0. So we're going to try the same thing here. The only hope we have is that somehow this just magically factors and we're good. So I always like to keep the highest exponent term positive. So I'm going to put everything on the right. So I'm going to have x cubed minus the x squared plus 2x minus 2. Now, whenever you have 4 terms, the kind of factoring you always want to try is factor by grouping, which means you factor what you can out of the first 2, and then what you can out of the last 2, and then hope that you see a pattern. So let's look at the first 2 terms. What can I factor out of both of those? What do they both have in common? X squared. If I factor that out, I'm left with x minus 1. The goal is to get x minus 1 again. If we do, then we can solve. Does anybody see what I can factor out of the last 2 terms? 2. If I factor out a 2, what am I left with? I'm left with x minus 1 again, which means factor by grouping is going to work. So now we look at that term and that term and look at what we see that they both have in common. What do they both have? They both have the x minus 1. All right, so I'm going to factor that out. If I take away the x minus 1, or if I pull it out of the first term, what's the only thing that's left in the first term? X squared. So you write that down. And you have a plus sign. And what if you take the x minus 1 out of the second term? What's the only thing that's left? 2. So now we have something times something equals 0. We factored it. So if you're going to multiply 2 things together and get 0, one of them has to be 0. Either this one or this one. Okay, how would you solve the one on the left? Yep, just add 1. There's your answer. Let's check the one on the right. You would minus 2. And then what would I have to do to both sides to get x alone there?
When you square root,
I would square root, but what's the problem?
-2.
Okay, why can't I take the square root of negative 2?
It's a negative number, you can't square root of a negative.
Yeah, this would be imaginary, so we don't get any solution from that part. If it had been x squared equals positive 2, we would have been okay. But it's not. So it's x equals 1, and if we check it, if we plug it in the original problem, I'll just move away the stuff that wasn't the original problem. Let's put that down there. If you plug in 1, you get 1 minus 2 times 1 plus 2 equals 1. And that's all cube rooted. Well, minus 2 plus 2 cancels out. And then we end up with, does the cube root of 1 equal 1? Yes. So our answer works. Any question on how we got 1?
That would be your light starting. What would is that just like the solving of it?
So this is just solving. Yep, we're not doing any graphing. I would not have you graph something like this. If I was going to have you graph it, it would have to be more like that. And I would get rid of all that. So now it would just be a shift and a stretch. But with that x squared, it would make it too complicated to graph. All right. This one, we're just going to solve algebraically. I'm not going to graph it. Graphing it would be easy. If you want to know how to solve it graphing, just put all of that in y1, put all of that in y2, and just see where they cross. Second, calc, intersect. So graphing, we've done that before. But let's look at solving it with algebra. How many roots are in this problem?
Oh.
Yep. 2. So what that means is we're going to have to use powers twice. Okay. One of them, it will get rid of the first root, then do it again to get rid of the second root. Now, directions say isolate a radical. Do we have a radical by itself on one side? No. You have 2 radicals on the same side. So I'm going to just take one of them and move it to the other side using addition. That's going to leave this by itself on the left. So I get that. Equals 1 minus square root of 4x plus 9. Now I'm ready to get rid of a root. Isabel, what am I going to do on both sides?
First, I have a question.
What's your question?
Nothing.
Okay. Thank you. All right, so now I have a question. The same question. What am I going to do on both sides to get rid of a square root? Square it. Okay. On the left, that's the easy part. Okay, when you square it and square root it, this and this just cancel. Now on the right, I'm going to square that. But I'm not going to write it as an exponent of 2 because you need to kind of see this out. I'm just going to copy it again. Remember, writing the same thing twice just means an exponent of 2. But I wrote it out the long way. Because what do you think you're going to have to do there when you square that? What do you think you're going to, how do you think you would do that out? Well, how would you do out something like 3x plus 2 times x minus 5? Well, it's factored, so we're doing the reverse of factoring, which is what? FOIL, right? Distributive property. We have to multiply it first, outer, inner, last. Since we're multiplying the same thing times itself, it's not too bad. So we'll start with 1 times 1, which gives me 1. Gets harder, so stay with me. 1. We have 1 times the square root of 4x plus 9, we have another 1 times the square root of 4x plus 9. So how many square root of 4x plus 9s is that? How much? 2 of them. So you have 1 times something, 1 times the same something. That means you have 2 of the somethings. So 2 of the 4x plus 9s. All right? If it's confusing, just think of this as a box. Think of this as a box. 1 times box plus another box is 2 boxes. And what's in the box? 4x plus 9. Now the last part. The square root of 4x plus 9 times the square root of 4x plus 9. What's that going to be? It's the square root of 4x plus 9 times the square root of 4x plus 9. It's almost like you're just squaring the square root of 4x plus 9. So what would happen? It's just 4x plus 9. Now, if we look, it looks worse, but it's not, because we've got some like terms, 1, 4x, and 9. All of that can be moved over to the other side. Okay. So that's what I'm going to do. What could I subtract from the right side to move the 1 and the 9 over to the left at the same time? Yeah. 10. If you subtract 10 from the right, that's going to cancel the 1 and the 9, because 1 plus 9 would have been a 10. And we have to subtract it here. Something else I can subtract from the right side and move over to the left. Yeah.
4x.
4x. So I can cancel that. So I've just gotten rid of 3 things on the right-hand side. So right-hand side's a lot simpler than it was. 2 square root 4x plus 9. 6x minus 4x gives me 2x, and then 12 minus 10, 2. So it's getting much simpler. I need to get rid of this radical. The only way I can get rid of it is if it's alone. It's got a times 2 in front of it. So how would I get rid of that 2 on the right-hand side and put it over on the left? See it?
Divide both sides by 2.
Yeah. Just divide both sides by 2. And remember, when you divide by 2, I write it everywhere, so I remember to do it everywhere, and it cancels everywhere. Gone, gone, gone. So now I just have x plus 1 equals the square root of 4x plus 9. Now I can get rid of that square root by squaring both sides, and from here we've done the hardest part. Okay, I think the hardest part is right here, when you FOIL. Right, so let's square both sides one more time. Square, square. What am I left with on the right when I square both sides? Yeah.
X squared plus 1.
Let's start with the right. I'll come back to the left. That's part of what's going to be on the left. We're missing something. But let's start with the right. It's easier than the left.
4x plus 9.
Just 4x plus 9. They just cancel. Now, I see where you got the x squared plus 1. You squared this and you squared this. But remember, x plus 1 squared means this. So what are we missing that should be in the middle when we square x plus 1? Yep, 2x. Yep. And now we have an equation without any roots in it at all. And what's the highest power in that equation? 2. It's a quadratic, so we can solve it. We either can use quadratic formula if we had to, or once we put everything on one side, it will probably factor. Okay. In fact, it will. So let's do x squared minus 2x minus 8. So So I subtracted the 4x, and I subtracted the 9. All right. So two numbers that multiply to give me 8 and subtract to give me 2. 4 and 2. So we're going to have an x and an x, 4 and a 2. And my signs are going to be plus minus. Let's try plus minus. X squared plus 2x minus 4x. Yeah. Looks good. What would make the first factor 0? 4. And the second factor? Negative 2. Now I'm going to go back up and make sure that they both work. If you plug in 4, let's check. What's 6 times 4? 24 plus 12. And the square root of 36? 6. Minus 4 times 4? 16 plus 9. And the square root of 25? Does 6 minus 5 give you 1? Yeah, that one works perfect. The negative 2. 6 times negative 2 is negative 12 plus 12. And the square root of 0? 0. 4 times negative 2. Negative 8 plus 9 is 1. What's the square root of 1? 1. Is 0 minus 1, 1? No. That answer didn't work. If you forgot to cross that out, you'd lose a point. You wouldn't get the whole thing wrong, but you should just remember to cross it. Okay. So that's the hardest kind of root problem we have. Okay, the 2 roots. Okay, so homework tonight is on 255. It's 5, 6, 12, 14, 20 to 22, and 28, 31, and 35. So I think it's like 9, maybe 10 problems. Okay, so we'll take a look at that tomorrow.